when a technique is devised to manage a waste, be it metallurgical or otherwise, it begins with understanding the chemical makeup of the waste. When you have two different waste with overlapping chemical composition, then the technique adapted to manage one waste can be extended to that of the other. So primarily, the ways to manage a given waste depends on its chemical makeup, and there is an overlap in the chemical makeup. The techniques to manage them can be shared. So in this discussion, we have a blast furnace slag and the steel slag. Both of these slag have significant overlap in their chemical makeup, except for that the steel slag has few additional components to it. So because of the overlap, the techniques adapted to manage blast furnace slag can be extended to that of the steel slag, and correspondingly steel slag can be used in the manufacturing of concrete. Now concrete primarily comprises of three components: aggregate, cement, the binding agent, and water. Now it is the aggregates that offer strength or substance to that of the concrete. Now because of the similarity in the composition, the blast furnace slag has been replacing, the aggregates, can now be replaced with that of the steel slag. The steel slag replaces the minerals essentially that constitute the aggregates. Now in general, when there is in a conventional concrete, these aggregates are made of minerals, and when you replace these minerals with that of the steel slag, it offers primarily an economic benefit. Now given that it is these aggregates that offer strength and whatever substance that is required to that of the concrete, it is vital for us to compare the strength offered by the concrete when these aggregates are replaced by the steel slag, and it is found that both strength and hardness of the concrete that is made of, or that is includes or accommodates steel slag, is comparable with a conventional concrete that is fully made of mineral based aggregate. And on top of it, it is noticed that owing to the presence of iron oxide in the steel slag, the abrasion resistance offered by the corresponding concrete is significantly higher when compared to the conventional concrete, and also concrete with blast furnace slag in it. For instance, if you have two different concrete, one with blast furnace slag, the other with steel slag, the abrasion resistance or the wear resistance offered by the concrete with the steel slag is noticeably higher when compared to that of the blast furnace slag. This is primarily because of the presence of the iron oxide. Now, besides iron oxide and magnesium oxide, there are other components that differentiate the chemical makeup of the steel slag from that of the blast furnace slag. So you have enhanced presence of calcium in different forms, silicon in different forms, and finally phosphorus. Because of this a distinct makeup of the steel slag when compared to that of the blast furnace slag, its application or the way it is managed also varies from that of the use of the blast furnace slag. For instance, because of the presence of calcium in the form of calcium oxide in the steel slag, this calcium oxide acts as lime under definite conditions. So correspondingly, the steel slag is used to manufacture clinkers. Now the clinkers are the foundational agent for cement manufacturing. So when you are manufacturing cement, the mixture of limestone, clay and other additives are grinded and they are heated at high temperature, ultimately giving us clinkers. So these clinkers form the foundation of the cement, and they start from limestone, clay and other additives which are grinded, mixed together and heated. Now because calcium oxide that is found in the steel slag act as lime, we can use the steel slag as a raw material for the clinker. So ultimately, when you produce a given amount of clinker using steel slag in them, the amount of carbon dioxide released is significantly reduced. So the amount of carbon dioxide released is proportional to that of the amount of these mixtures that are heated up. Now, when we include steel slag in it and produce greater amount of clinkers, then the use of steel slag reduces the amount of carbon dioxide that gets released into the environment. Now, of course, blast furnace slag also played a role in reducing the carbon dioxide from the cement manufacturing, but that was rather indirect. We were able to replace glassy slag or blast furnace slag with the cement, so the amount of cement consumed got reduced, ultimately reducing the amount of cement that is produced and ultimately reducing the amount of carbon dioxide that is released during the process. However, in steel slag, because of its enhanced composition of calcium oxide, we are able to introduce steel slag in the raw materials of the clinker. That means ultimately when a given amount of cement is produced, the amount of the carbon dioxide release is decreased because of the introduction of the steel slag. And on top of it, again owing to its distinct chemical composition, the steel slag has an hydration property that is similar to that of the cement. So therefore the steel slag is used as a secondary cementitious material. Now here it is not used in the formation or in the production of clinkers, but it is used to supplement the clinkers in the production of cement. So it means we have going to have an enhanced amount of cement, not purely from that of the clinkers, but the combination of clinkers and steel slag. So ultimately the amount of carbon dioxide released to achieve this enhanced formation of, or the enhanced amount of cement, is less when compared to the conventional techniques. So to boil it all down, you have two ways in which the steel slag is directly involved in cement manufacturing. Both of these ways reduce the amount of carbon dioxide released for a given amount of cement production. The first way is the steel slag is introduced in the mixture of the raw materials that ultimately turn to clinkers. The second way, we are complementing the clinkers that are produced with steel slag by treating them as a secondary cementitious material, and both these are possible because of the distinct chemical makeup of the steel slag from that of the blast furnace slag. Now one other rather intriguing example in wherein we can introduce the steel slag is generating or manufacturing something called as a high dense concrete. Now the application of this high dense concrete is interesting because this high dense concrete is employed to shield radiation. So the source of the radiation can be a nuclear reactor, whatever it is. The high dense concrete are manufactured, they are produced for the primary purpose of shielding the radiation. Now high dense concrete essentially demand high dense aggregate. Now again, in order to achieve these are not like normal aggregates, so it means that we are going to look for minerals that will satisfy certain conditions, and correspondingly the cost of this concrete is going to increase. But now we are able to build this high dense concrete by replacing the aggregate with the steel slag. And when we replace the aggregate with steel slag, the way we understand the shielding property is by performing an experiment such as this, wherein we have the concrete sample here, which includes rather the steel slag, and this is a high dense concrete which is proposed to shield the radiation that gets generated from the cesium source here. And as you can see, with increase in the steel slag, the absorption of the radiation significantly increases, and the radiation that gets out on the other side that actually gets detected decreases. So what you observe in this plot is the amount of radiation that gets detected on the other end. So when this decreases, what it essentially means is the concrete does a very good job of shielding your radiation, and this is achieved by reducing the amount of specific high dense mineral and mineral aggregates with that of our steel slag and with some steel shards in it. So the steel slag can now be used to generate or manufacture a special form of concrete, as opposed to that of the regular concrete wherein blast furnace slag can be used. The steel slag can be used to generate a special form of concrete that can be used for shielding radiation, like gamma radiations. Now, in addition to this application, there is another form of concrete wherein the steel slag can be employed. So the general concrete, the conventional concrete that is employed for building comprises of cement, and when we replace cement with asphalt, we have an asphalt concrete that is employed, that is used in the construction of roads. And even in these asphalt concretes, we have different forms of aggregates, and these aggregates can be, or these mineral aggregates can be replaced with the steel slag. So here the structure of the concrete remains the same, except for the binder is now that of asphalt compared to that of cement in the conventional case. And now we replace the aggregates of the asphalt concrete with that of our steel slag, and ultimately we are able to achieve the required abrasion resistance and also skid resistance. Of course, in this case, more than that of the mechanical properties, these resistance play a critical role, and because of the unique composition, the differentiating composition of the steel slag when compared to the blast furnace slag, steel slags can be employed in these applications as well because they offer good abrasion and skid resistance. When you compare or when you consider what constitutes a ceramic, these are the building blocks of the ceramic. So when you consider anything that is made up of ceramic, it is usually made of these building blocks here. And when you look closely and boil them down into their chemical composition, they have a chemical composition that is similar to that of our steel slag with a greater amount of iron oxide present in them. So you have the raw material that is used for making any ceramic utensil or any ceramic component. You compare that composition to that of the steel slag, they significantly overlap. On top of it, in steel slag, you have an additional component in the form of iron oxide. So it means based on the steel slag or including the steel slag into these components, into these raw materials, you will be able to build or manufacture, synthesize ceramic components. And this is one other technique using which the steel slag can be managed, that is by using it in the fabrication of ceramic component. And because of the different or the enhanced chemical makeup the steel slag has in the form of iron oxide, it improves the workability of the ceramic that has steel slag in it. The presence of iron oxide makes the entire mixture of the raw materials more viscous at relatively low temperature, making it more workable. And at the same time, the strength offered by it is increased because of the presence of iron oxide. And finally, the sintering temperature is reduced so that the less amount of energy is required when we are manufacturing this ceramic component. So there is an overlap between the raw material of a ceramic component to that of the steel slag. So therefore, the steel slag can be replaced these raw materials or can be added to that of the raw materials, and we do that, we have increased strength, a greater workability and reduced sintering temperature, thereby making the entire operation more efficient, at the end of which you have a strong and also a different forms of ceramic components. Apart from that, it is also possible for us to include the steel slag in the manufacturing of something called as a microcrystalline glass. So these microcrystalline glass are largely used in decorative purpose or for decorative purposes and also for utensils. So these microcrystalline glasses, so glasses generally are amorphous in nature, but these are not completely crystalline, but they exhibit crystalline order locally. So these are referred to as the microcrystalline glasses. So one advantage of microcrystalline glasses, or the primary advantage we have in microcrystalline glasses, is that they tend to combine the good properties of both amorphous and crystalline material. They tend to combine the properties of, to a certain degree, of both solid, rather metal and that of the non-metals, so particularly glasses. So glasses are often offer chemical resistance and also wear resistant. But when you have in the framework of glasses a short range order, a crystalline structure embedded onto them, so you also achieve a good thermal stability and mechanical strength. Now such microcrystalline glasses can be achieved when we infuse the ceramic with or the raw material of glasses with the steel slag. And the reason why we are able to achieve is again because the iron oxide or the presence of iron in the steel slag, they act as the nucleation sites for the crystals. And these crystals are essentially what offer a short range crystalline nature to that of your glass. So ultimately you are producing a glass with microcrystals in them, and these crystals require a nucleation site, and these nucleation sites are offered by the iron oxide that is present in the steel slag. So when you have a raw material that is used for manufacturing or synthesizing glass and you add steel slag to them, you end up having something close to a microcrystalline glass with these enhanced properties. Now, as opposed to all these applications, an efficient way of waste management that we saw while considering blast furnace slag is that these wastes can be used to tackle or neutralize other forms of waste. So given that the chemical makeup of the steel slag is similar to that of the blast furnace slag, the same approach or the same role can be expected of the steel slag as well. So we saw that the blast furnace slag, or in our previous session we looked into how the different ways in which the blast furnace slag can be employed to manage different forms of waste. Because of the overlapping chemical composition, the same can be expected of the steel slag as well, and it has been proved that whatever blast furnace slag can do, particularly in managing the other forms of waste like heavy metal adsorption or trapping CO2 emission, it can also be achieved by the steel slag as well. However, one different waste that can primarily be attacked by, or that can primarily be managed by the steel slag, is hexavalent chromium. So hexavalent chromium is rather the most hazardous form of chromium that gets released into the atmosphere when chromium or chromite is being mined. Now, this hexavalent form of chromium, which is hazardous in nature, can be managed efficiently when we use steel slag to manage them. So these are the ways in which steel slag traps the hexavalent chromium. So it begins by changing the valency of the hexavalent chromium to that of the trivalent chromium. So the first step begins by changing this valence state from that of hexavalent to that of trivalent when this chromium ions are exposed to steel slag. So once you have this change from hexavalent to that of trivalent, so what ultimately happens is you have a precipitation happening. So you have the sequence of reaction that primarily involves that of change from hexavalent to that of trivalent chromium, and once you have a trivalent chromium, you ultimately have this trivalent chromium getting transformed into a precipitate that gets locked down and it is not spread across the atmosphere, thereby causing hazardous effects. So steel slag can ultimately be employed in regions which is contaminated by both trivalent and hexavalent chromium, and by deploying the steel slag, they transform these hazardous hexavalent chromium into precipitates. Through precipitation, it restricts the harmful effects. It changes the hazardous form of hexavalent chromium to something that is non-hazardous, and it traps them, it localizes them. So this is one hazardous agent that can be efficiently handled by the steel slag when compared to that of the blast furnace slag. Whatever blast furnace slag does, steel slag can also do it. But this is something that is more efficiently done by steel slag when compared to that of the blast furnace slag, that is use precipitation to trap in the hazardous forms of chromium. Now, besides hexavalent chromium, these are the ways in which the steel slag can also manage the other heavy metal ions. So this expression here, this equation here, they represent essentially the ion exchange process. So your calcium ion is getting replaced by the heavy metal ions. So essentially you are trapping in your heavy metal ions by giving away your calcium ions. So this is something we have seen that can be done by the blast furnace slag as well. The same is getting replicated, or the same is done by the steel slag, but since it has the increased amount of calcium in it, the efficiency of using steel slag is noticeably greater than that of the blast furnace slag. And besides that, similar to that of the blast furnace slag, formation of complex metal complex is possible when we deploy steel slag as well, and ultimately these complex they tend to get stuck to that of the surface, thereby reducing the bioaccessibility. So whatever blast furnace slag does, steel slag essentially does it in a more efficient way, owing to its primary difference in the composition and increased amount of calcium that is present in it, and also iron that is present in it. So calcium and iron essentially improves the way these steel slag they trap in heavy metal ions when compared to that of the blast furnace slag. Now finally, one interesting place or area wherein the blast or the steel slag is deployed is in the marine engineering, because the steel slag has the components that can enhance the growth of plants, that can enhance the growth of crops in an agricultural field, in the field of marine engineering, particularly in the bed of water body or in the seabed. These steel slag, when they are used, they allow for the growth of algae. So underwater vegetation is possible. The growth of certain forms of algae becomes possible when we deploy the steel slag into the water body, at the bed of the water body or the seabed. And when you have a thriving growth of algae, the other microbial organism tends to grow along with it, thereby attracting a new marine ecosystem. So therefore, in the existing water body or in sea, the steel slag, of course, after proper treatment, they are getting deployed. They get deployed essentially to enhance the marine ecosystem, allow for different algae to grow, and thereby ensuring that the ecosystem thrives in the water body. And not only that, instead of using a natural water body and then deploying the steel slag onto its bed, artificial setup is also generated. Artificial setup are also built for the purpose of marine engineering in order to generate such an ecosystem in an artificial setup as well. And these artificial setup, the substrate of it, they comprise of the concretes that include significant portion of the steel slag. So when we are building artificially a bed for the microbial organism to thrive, this bed will be made of concrete that includes significant portion of the steel slag, and because of the composition of the steel slag, they improve or they allow for a significant growth of the algae, primarily because of their composition. The composition of the steel slag encourages the algae to grow, thereby allowing a thriving ecosystem of different microbial agents. So because of its enhanced composition, because of its distinct composition from that of the blast furnace slag, steel slag has a greater reach when we talk in terms of its management. So starting from, if we go in reverse, starting from marine engineering, we also saw that the steel slag can be employed in nuclear application to build or to manufacture high dense concrete which can absorb the radiation. We also saw that the use of steel slag can essentially improve the efficiency of or the productivity of your crop. So even though there is a significant overlap, the steel slag, because of its composition primarily in terms of iron oxide and calcium oxide, can offer an efficient way of management, particularly when we are focused in cement manufacturing or that of concrete, an efficient way of managing when compared to that of the blast furnace slag. So with that, we are winding up our discussion on the steel slag. Goodbye.